And now we're having a summary of the day's proceeding by Dr. Francis Dock, and so we're going to listen to him and his 2 slides. And after that, we've agreed that we will be happy also to open the floor of people to make comments about the day and what they learned today, and if they want something to share with the rest of us. Okay, thank you.
Thank you. And thank you very much for this invitation to provide the summary. I have to tell you, this is a bit of a challenge. I learnt this evening that some people who do summaries actually type up slides during the day. That I hadn't even thought of, and I don't think I would have done it even if I'd thought of it. So I do have 2 slides. What I'm going to try and do, I'm not going to review each of the talks individually. That would be impertinent of me. You've all listened and you've learnt, and you will have absorbed your own particular interpretations of those 5 quite excellent talks. I must applaud now, because I'll probably forget at the end, all 5 speakers and Joe, the organiser, and so on. I'm saying that now just to make sure I remember. I thought I tried to find 3 possible themes. One is obviously the historical theme. And in Stephen Keevill's talk, he was talking about trying to identify the origin of medical physics. And I wrote a book about 10 years ago called Physicists and Physicians, and I think I identified, and I'll tell you where I think the start of the term medical physics is. It was in France. They, of course, said physique médicale. And after the revolution in France, when they had to recreate medical training, the first professor of medical physics and hygiene was appointed in the Faculty of Medicine in Paris. And he wrote a syllabus about physics and hygiene to be taught to medical students. And about 20 years later, he was still that professor, and he defined medical physics. Physics, first of all, it's applied, it's not theoretical. And it's applied to the knowledge of the human body. Now, we've heard aspects of that. That's biophysics. The last talk most excellently demonstrated physics applied to the knowledge of the human body. Let us dig deep to work out how cells and biochemistry and the physics of a body works. The second criterion is to its preservation. I like that. He was actually rather worried about pollution in Paris at that time. That was rather bad. He was also worried about vaccination, which he tested. Preservation, physics applied to looking after the human race, has kind of got lost, hasn't it, from medical physics. But it's nevertheless still in climate science, in ecological management, a very definite place where physicists can ply their trade. And obviously to the treatment of illnesses. He didn't say diagnosis either, interestingly, while we've had Martin tell us a lot about the history, which was specifically diagnosis through medical imaging. I think there is also a social... this was 1814. What did he mean about physics? Well, he certainly knew about temperature rise. He knew about biomechanics. Biomechanics really emerged in the 18th century. We heard about Sanctorius. Somebody mentioned Sanctorius. Anyway, I've lost who it was. Sanctorius, amazing chap. Oh, I know about Sanctorius. Sanctorius did 2 things. One is he developed an air thermometer. He also did the first physiological measurement. He did a series of measurements about body weight and related body weight to health. beginning of the 18th century. Borelli, same time, middle of the 18th century. He was an astronomer, and he wanted to apply mathematics to the workings of the body. He also used a thermometer to determine a question: where did body heat come from? Because it was supposed to come from the heart. And he took a live animal, a spirit thermometer that were just becoming available, thrust it into the heart of this live animal and compared that temperature with the temperature in a muscle. Discovered they were the same. The heart was not the source of body heat. Measurement is in there. In physics, measurements are part of the development of medical physics and go back a very long way. This is a bit of the history that I'm going to add in because it got missed out. I think the 18th century was the century of biomechanics. Sorry, I'm getting the wrong. The 1600s, the 17th century was biomechanics. If you characterize the 18th century in any way, I would say it was the century of bioelectrics. Muschenbroek developed his Leyden jar. At last, you could carry electricity around, and immediately, Abbé Nollet was shocking people, treating palsy. Immediately. This was the first time that dramatic link between a physics development and something in medicine is very obvious. The second time was Röntgen's first paper on the new rays. That's an extraordinary paper because it explicitly links medicine with physics. Very unusual. We learned about the development of MRI and the latency between the original chemical studies of MRI and it's being used for imaging. A similar thing happened with ultrasonics, developed in the First World War, not appearing for medicine until the 1950s. The timings of physics associated with medicine have been mentioned today and I think are very interesting. And indeed, a point was made I'm just trying to think who it was. Martin Graves made an interesting point about whether MR would have developed at all if it had been timed in a slightly different way. I've also heard it said that maybe if CT hadn't happened and radiologists have become sensitized with cross-sectional imaging, maybe MR, nobody would have invested in MR because it wouldn't have been seen to be a diagnostic modality that would take off. And while I'm talking about imaging and what Martin Graves had to say, being an ultrasound person, I have to say that cross-sectional imaging was there, embedded in the medical profession before CT came along. And I only say that because I'm embedded in ultrasound and I need to wave the flag. But it didn't make any difference to the fact that when cross-sectional images appeared, X-ray cross-sectional images for CT, the medical profession, some of them at any rate, were very cautious. There isn't a porosity between disciplines within medicine. And you have to realize that ideas are regenerated. So when I was thinking about what to say, I was thinking about three themes. I've dealt about historical perspective. I thought I could say about metrology. I thought everybody would say something about measurement. I knew Graham Machin was going to talk about thermal metrology, works at the MPL. This is the message. And I kind of assumed that message would appear elsewhere. And I note its absence. Measurement was almost not mentioned by any of the speakers. This is no criticism of the speakers, by the way. I think they're magnificent. But you miss things if you look for them. And physics is nothing if not a measurement science. Or maybe it's just so obvious. I mean, we measure height, we measure blood pressure, we measure weight. They're all part, maybe they're embedded. But I know, because I can remember CT images of printed numbers of X-ray attenuation coefficient on an old printer, that aspect of CT disappeared. Nobody talks about relaxation times in MRI. At least some people do, but mostly it's those unbelievably impressive images which sell MRI. And I think that perhaps physicists could try a little bit harder, or maybe the communication with our medical colleagues might be a little bit stronger to appreciate that actually numbers are quite useful. Going back to my original definition, when Allais was writing that definition at the beginning of the 19th century, he was certainly thinking about heat, he was thinking about electricity, he was thinking about mechanics. They would have been embedded in the physics of the time. What would not have been there is bioenergetics. The concept of energy embedded in the thinking of biological systems was not there. It evolved very slowly during the 19th century. And if you were a doctor and explaining things around 1800, you would have explained life events by vitality. Vitalism was the way you explained things. By the end of the century, by 1900, that had been swept away, and it had been swept away by physics. It had been swept away, obviously, we know James Prescott Joule's quantification of the mechanical equivalent of heat. But in fact, that didn't really apply to medical things. It was Helmholtz in Germany, and who had been trained as a doctor and then became a physiologist and a physicist. And a guy called Julius Robert Mayer, who was a doctor and everybody ignored. And extraordinarily, he understood in, I forget, about 1847, that there was something, I'm not even sure he called it energy, that started at the sun, arrived on the leaves, was processed into vegetation, was eaten by the animals, digested into a chemical form which resulted in heat and force in their muscles. Now, I find that quite spine-tingling, that he could have conceived that whatever it was, energy, in those different forms, came right through. And I found the lovely link this afternoon in the last talk, where Mayer, in the middle of the 19th century, had no idea how photosynthesis worked. He just knew that there was an energy transfer there that was necessary. And it's taken until now to have a plausible alternative explanation of photosynthesis on the basis of quantum biology. The other example is he didn't know how muscles worked. It didn't matter to him understanding the conversion of energy that he didn't know how muscles worked. And in fact, that was a triumph of microscopy, which is Kim Hardy's lovely overview of the way in which physics steadily improved our ability to investigate more and more deeply biological processes. And the actin-myosin links were, I believe, only shown by the advent of the electron microscope. So that was pretty well a century later. So some of these processes work immediately, some of these knowledge transfers work very fast, some of knowledge transfers work very slowly. Looking into the future, therefore, I'm deeply confident in what Alexandra Castro was saying, that there is deep knowledge there to be explored. If I were to be asked about where a young physicist might seek out their future, that would be one of the options, coupled with a deep enthusiasm to explore and find out, not that they're just fed information. So that was the cream on today, I have to say, for me. Thank you. And that's the obvious future to emerge from today. There are others. It's difficult to know. I sense, in answer to an explanation, to a discussion about whether there's more imaging. I guess there is. I feel maybe there's only going to be tweaks in improved imaging. And indeed, one of the problems with imaging is that the recipients of that information, or that imaging information, those who are charged with its interpretation in order for the care of their patients, are being swamped with information. So there, I think we have to look to our artificial intelligence methods to, in some way, assist with that distillation of this extraordinarily large amount of information that is now available. As I said, one of the aspects of physics applied to medicine is in environmental science, the maintenance of health rather than its treatment. And I think it may be, we know because it's being discussed, that is where there's a lot of discussion, that we maybe have got to the point where we've striven hard enough to deal with illness, and we now have to care for the human race in a better way. And maybe that's where some physicists should be pointing their efforts. Now, I think that is as best I can do to try and draw today together. And for the speakers, if I've left out a particular pet topic, I do apologise.
I'm going to add a comment on the future, something coming out of the labs these days of biophysics. For many years, autoimmune diseases were thought that they were not treatable. And traditional pharmacological methods, they just try to maintain the patient the best they can. There's some beautiful results in the last months. Because of physics and collaborations between medics and physics and biomedics, people have been starting using nanoparticles in medicine. You all have the COVID vaccines. And one biologist, a bit by chance, put nanoparticles, he was not really thinking what he was doing, iron oxide nanoparticles on cells, autoimmune cells. And he realized that his mouse, he was treating a mouse with autoimmune disease, suddenly stopped the autoimmune disease, did not have any chemistry. This is a result that many physicists that work in mechanics of cells sort of somehow predicted. That is, the mechanics of the cell, of the immune cells, that are probably its target for medicine. This is great news, because now finally, the biomedical community, who never listened to the people working in mechanics in biology, are paying attention. And there's articles in Nature and Science talking, oh my God, we might be finding a cure for autoimmune disease. And it will come from physics, which is great news. And that was my comment on the future. If someone else wants to comment on something they learned or something they loved about this day today, or whatever they want to share with the rest of us, please here.
Could I just make a brief comment to see, is there no way forward in imaging? No. Oh, sure, thank you.
The way forward to imaging.
Yeah.
Yes. Medical imaging.
Yes, medical imaging, yeah. Just a short comment. We have used thermal imaging in the past, which wasn't mentioned, but some people have started using it again and seem to be making some progress with it. Some people also tried light imaging. It seems to have just fallen into the doldrums. But the thermal imaging looks promising. The other thing about potential new developments which could come is we now have magnetoencephalography and magnetocardiography. And if we could use those and integrate the results with imaging, with AI, then I think there is a possible way forward for further work. And I think that hasn't been explored yet. I think that's where we should be going. Thanks.
I'll comment on that. One of the problems of AI, and that I think biophysics will also have a solution for, is energy. AI uses an enormous amount of energy, and all this explosion of application is threatened by two things. You cannot make the chip smaller, you cannot get the transistor smaller than 2 nanometers, and actually the amount of energy used by AI, I think, doubles every 100 days. So it's becoming but biology computes without energy. And now, finally, biological physicists like me are trying to convince people to learn from nature, learn how to compute with noise, what I was saying before. So more avenues for the future of physics, learning how to compute like biology does without energy, especially of complex systems. More comments? Yes?
Well, you identified one quite subject that wasn't that much heard here, was metrology. And the other one is really the role of data. As we have more collaboration between physics and the medicine, and AI is coming there, we have masses of data. And I wonder if you have any opinion on the role of data in the future in this complexity.
People who are closer to that than I am now, I have to say I'm on the margins of being able to discuss it, might comment. My only comment is that ultimately, whatever is distilled out, okay, my concern is the data-human interface. That somehow you, as the recipient of either all that data or something distilled out of that data, must be able to draw it into your mind and distill it. And that feels to me to be a bottleneck.
I agree. Humanizing the way we deal with all this data is going to be very problematic.
Frances, that was fantastic. And I agree with your comment about human life preservation. And I think we're coming full circle. And my great-grandfather used to be with a pathician in India. And the way he looked after the village people was prevention. They paid him money every month to keep them healthy. Any time they were unhealthy, he didn't get paid. So now going forward, we should be in a situation where we have personal dashboards that we have measurements of our vital statistics and vital biologies and physiological measurements, and it keeps a track of what's happening. And as soon as it wavers from something that is going to be indicative of an illness, it should be immediately raised up. And I think that's where we should be going.
You know, Sanctorius, in one of his aphorisms, says very specifically about weight. The absolute weight doesn't matter, but if the weight goes up or goes down, back then in 1610, he knew that actually that kind of stable monitoring and that's a very particular aspect, but more generally, I couldn't agree more.
Thank you. Thank you. One of the questions that I liked as a retired GP was the question as to whether AI was going to take over in terms of managing our patients. And I reflect on the fact that as a medical student, I learned all sorts of stuff about anatomy, particularly auscultating the lungs and all the different lung segments, and still had to remember them and describe them. And through my life, I've seen the move away from the face-to-face management of patients, and never more so apart from in the crisis of the pandemic, where now practices are trying to move back to that kind of face-to-face. And my thesis is that there will never be a substitute for the private consultation, the face-to-face interaction, and the hands-on approach, even if it's just simply touching your patient to let them know that you have connected with them. And that moved me on to the other very interesting point that the last speaker raised, that she gave the example of the concept of coherence. The other thing that I have observed during my life in science is the movement, the increasing congruency, if you like, between the different disciplines, which I think's obviously now becoming clearly more essential as we hear in today's presentations about the wonderful overlapping between departments, and that I would have thought in your future was an essential.
I would have thought that concludes today's events, don't you?